Thanks, Jeremy, for the presentation. As he said, I'm Yahya Boye. I'm a PhD student at Paris PSL. And today I will present our work on the flexibility method for contact mechanics using FEniCSx. So contact is everywhere in our daily life. We experience it while walking or shaking hands with people. But it's also crucial for many industrial applications. For example, tire road contact, wheel rail, gears. However, even in the pure simplest case, it's a very difficult problem to deal with, mainly due to its nonlinear and non-smooth nature, I'll say. So to formulate the unilateral frictionless contact, we make use of the so-called Signorini-Moreau conditions. So it just express basically three physical intuitions. No penetrations. The gap between the bodies should always remain positive. No adhesion, so the contact forces are always compressive, and complementarity. When one exists, the other vanishes. And these conditions are equivalent to the KKT conditions in optimization. The weak form is quite similar to the one that we have in linear elasticity, but just with one more contact term, additional contact term, that's here denoted by TC, and the space that should satisfy the contact condition. So the TC depends on you as we should so, and it should be included in the bilinear form, not the linear one, as like for the Neumann data. And to solve this problem, several methods exist. We saw earlier today the TMC method presented by Pierre, but also there exist other ones. The penalty method, which is the simplest one to implement. So you allow penetration, and you regularize the contact conditions, and the contact pressure will be a penalty term times this penetration. So it's a kind of a spring that acts against the penetration. The cons of this method is that the penalty parameter is user dependent. So if you set it too low, you allow unphysical penetration. If you set it too high, it leads to an ill-conditioned system. The other method is the Lagrange multiplier method, where you enforce exact contact conditions through the lambdas, the Lagrange multipliers. And there is a problem here because you add new unknowns to the system, so it's an augmented system, and it's also a saddle point problem. The other family of methods is the augmented Lagrangian, which basically combine the previous two and which make it more robust, but also you still have the same cons. So let's imagine for a while that if you know the real value of TC, you can just put it on the right side and treat it like a Neumann data, simply. And this is basically the idea of the method that we are trying to revive, which is the flexibility method. And the idea is that you can write your gap as the trace of the displacement field, so the boundary displacement plus an initial gap. And in the linear regime, in linear elasticity and infinitesimal strain, this boundary displacement is linearly dependent on the contact forces with an operator that we denoted here by SC, which is basically the Neumann-to-Dirichlet operator for initiated people. And this leads to recasting your contact conditions to an LCP, a linear complementarity problem. You can solve this LCP independently from your global problem and get the contact forces and then apply them back to the global problem, the elasticity problem, as Neumann data. So this is what I tried to show here with this workflow. You construct this operator, you solve the LCP, and you apply the contact forces as Neumann data simply to your problem. To construct the compliance operator, the SC, the flexibility operator, there is a few ways. I present here two. The first one is via short complement. You just partition your stiffness matrix with the contact doves and non-contact doves. You apply a short complement and you take its inverse. The second way is an iterative way to do this. Is you apply a unitary load, the normal load at each contact dove, and get the displacement field all over the contact zone, and this gives you a column of your compliance matrix. And it's actually not that easy even if you construct this. There was a part in the workflow I showed you before that I didn't introduce, and the problem is that this operator, as you can imagine, is a fully populated matrix, is a dense operator, and this makes this method unscalable, so limited only to small scale problems. If you try to handle a large problem, let's say with 1 million DOFs with a dense matrix, you'll end up with 8 terabytes of memory, and to solve the LCP, it's a quadratic complexity, so unfeasible. So to render this method scalable, we need a compression technique. And the compression comes from, it's well known in the BEM world, I'd say, and it's hierarchical matrices. The idea is you start from your mesh and you hierarchically split it, partition it, to get a binary tree of clusters that will have a maximum size of n-leaf, parameter n-leaf. So the largest cluster in the mesh will have n-leaf, and we will get a binary tree by recursively splitting this mesh. And then we construct after that a block tree, which is basically the Cartesian product of this tree with itself. And each block of this block cluster tree will represent an interaction between 2 clusters. And the revolution with hierarchical matrices is the low rank approximation. So the idea is 2 clusters are far away. They will not really interact. So we can approximate the block corresponding by a low rank approximation. So this block, for example, the foot of Pikachu is quite far from its ear. And you can say if you press on its ear, hopefully his foot won't move a lot. So the corresponding block can be approximated by a low rank approximation. And you get a matrix that you store dense on the diagonal, and far-field interactions are stored in a low rank form. And this decreases the complexity for both storage and the MATVEC product to, from a quadratic to quasi-linear approximation. For the heat map is sure for different value of the admissibility parameter eta and n-leaf, we can reach 16 times compression, 16, 14 times speed up for MATVEC. The end goal of this project is to build a library based on this method that leverage its main advantage, which is non-intrusivity, to act like a plug-in library where you can just use a FEM library, for example, FEniCS, solve your contact problem in this library and have back the contact forces. So we have this, you could say in the repo I showed earlier. And in FEniCS, it's like a few lines more in code that we developed, so quite easy to do. I'll show here some examples. So it's a ironing test, simple ironing test, well known in the area. Just left, man. So this is a sphere sliding with a Dirichlet boundary at the bottom face. And we can also do it with a different type of indenters. No, that's it's already open here. And to validate the method, we used the most classical contact scenario, contact solution, which is the Earth solution. It's an elliptic profile. And you can see here the solution for the problem I showed earlier, where we have up here the numerical solution and the error. And you can see that by refining the mesh, you decrease the error. So this is an important example, which is a tire that we tried to simulate here with this mesh. And the good thing with the tire, it's that's an axisymmetric geometry. So with the sampling method that I showed earlier, you don't need to build the SC for all the contact zone. It's enough to build it just with one, let's say, clip of this. and only from that construct the whole operator. So this decreases significantly the construction of the operator. And these are some examples with contact between ground and tire. We can also extend it to bilateral contact, meaning having two deformables interacting. And the idea is just that the gap now doesn't depend only on the displacement of one body, but on the relative displacement of the two. And you will have like an equivalent compliance matrix that you can use for your LCP to solve the problem. And future work, hopefully, we can add friction and maybe also nonlinear materials. Thank you for your attention.
Thank you, Yahya. Any question? Yes, Paul?
Matrix compression, how do you construct this locality? Because I'm thinking about if you have multi-body contacts and you could use the connectivity based on mesh connectivity, then 2 points which later will come in contact might be considered far apart during the construction of your matrix approach.
This is the problem we're dealing with now, so we don't have a solution yet for it.
So if you have ideas. And the last question, maybe? No? Okay, so thank you again, Yahya.